Hello and welcome back. And now this part we're going to take our three fundamental gas laws, Boyle's, Charles, and Avogadro's, combine them together into one ideal gas law. This is probably the equation that you've seen, whether it's back in physics or in a chemistry class back in high school or something like that that you've seen before and that you've worked with before. So hopefully this ideal gas law is something familiar. So I'll introduce that to you, and then we'll go through a whole bunch of practice problems together to help you work with the equation, look at it just from a mathematical standpoint, and how we can use it conceptually, because again, understanding how these variables interact with each other without numbers involved is also very, very important into really understanding how pressure, volume, temperature, and number of moles all interact with each other. All right, so our combined ideal gas law is going to take our three gas laws. Pressure times volume equals a constant, volume divided by temperature equals a constant, and volume divided by number of moles equals a constant. And if this is all the same species, all the same gas molecule, all these constants are going to be the same. So we can combine these all together to form PV equals nRT. And this is our ideal gas law, where we have pressure times volume is equal to our number of moles, our R value, which is a constant, our ideal gas constant, and T, temperature, again in units of Kelvin. So our conversion here again is Celsius plus 273. That's how we get into our Kelvin temperature. So that's always something to pay very careful attention to. Our volume really typically needs to be in units of liters. Not always, but very often we want to make sure our units are liters, and pressure is typically in units of atmospheres. So paying attention to our unit labels is going to be very, very important, because we've got four different variables, P, V, N, and T, that we need to work with. Now, R value has a lot of different possible numbers associated with it, and almost all of these are just different because of the pressure unit. If you look at those, top one we have atmospheres, then we have bars, kilopascals, and the bottom we have torr. So that R value is just changing because we've done some dimensional analysis to change from one pressure unit to another. The second one from the bottom is in units of joules per Kelvin per mole. That one is a value for R that we often use when we're doing calculations with energy. So we're not going to use that R value for this equation, but anytime you see an equation that's dealing with energy, enthalpy, things like that, that's the R value that we want to use, 8.314. But for most of the gas calculations that we're going to be doing, we're going to use this top value, 8.205 times 10 to the minus 2 liters atmospheres per mole degree Kelvin. That's the value of R that we're most often going to be using with this ideal gas law. Okay, so let's get into some practice problems that I'll lay out for you. I'll give you some time to work on it, and then we can discuss. So this first one, let's estimate the pressure given that the volume of a tube is 5 liters, its temperature 27 degrees Celsius, and it contains 0.10 micrograms of nitrogen gas. I give you the R value. Here's our ideal gas law, PV equals nRT. So hit pause and go through and do the calculations and see what you come up with for an answer. Great. Let's see what we do. So first thing I like to do, because we have four variables here, I'm just going to make a list. So after I rearrange the equation and solve for the variable that I'm looking for to try to find pressure, I'm just divide both sides by volume, simple algebra to get that out of the way. I'm going to convert my temperature over from Celsius to Kelvin. 27 degrees Celsius plus 273 gives me 300.15 degrees Kelvin. Volume is in liters, so I can leave that as 5.0. Don't have to do anything with that. And I have to do some conversions there, because I was given a mass value for nitrogen. And first off, it's in terms of micrograms, so I have to go from micrograms to grams, and then grams to moles. So our number of moles is simply our mass divided by the molar mass. That first line in my numerator is I've already done my conversion from micrograms to grams. So I've changed 0.1 micrograms is 0.1 times 10 to the minus 6 grams. So I've done that conversion from micrograms to grams. And then the formula weight for nitrogen, N2, is 28.02 grams per mole. Nitrogen is one of those diatomic gases. So I just take my formula weight for nitrogen and double that. That's where the 28.02 comes from. And do that division out. I get an N value of 3.57 times 10 to the minus 9 moles. So now I have all of my numbers that I need. I can plug that into my ideal gas law and solve for pressure. So my numerator is now my number of moles, 3.57 times 10 to the minus 9. My ideal gas constant, 8.205 times 10 to the minus 2. And my temperature, 300.15 degrees Kelvin. That all gets multiplied together, and once that's done, then I can divide by my volume of 5 liters. I get a pressure value of 1.76 times 10 to the minus 8 atmospheres. So C is going to be my correct answer on this question. Okay. Let's look at another. And in this example, let's look at this question. The volume inside a pump is decreased from 100 cubic centimeters down to 20 cubic centimeters before air flows into the tire. Suppose that the compression is isothermal. Estimate the final pressure of the compressed air in the pump given an initial pressure of 1 atmosphere. So two things that we want to recognize. This term isothermal, that means constant temperature. And the other thing that we want to realize is that we're not changing the number of moles because we're not talking about adding or changing the amount of gas that we're dealing with. So our temperature is constant and our N value is constant. So I'll have you hit pause right here and work your way through this. There's a couple different ways you can solve this question. Take a minute and see what you come up with. All right, so when we solve this, I can look at the information and realize that this is really talking about one of our fundamental gas laws, Boyle's, Charles, or Avogadro's. But if I don't recognize that, I can use my ideal gas law and answer this question the exact same way. Right? So there's two different pathways we can take. I'm going to start with going through the ideal gas law. It's a little bit longer, but it has the benefit I only need to remember one equation. So what I need to do is I can do PV equals nRT for my initial volume of 100 cubic centimeters. That's my initial P1, V1 values. And then I can do it again under my second conditions when I've changed my volume. So I have two different versions of the equation. And what I'm basically going to do is set these two equal to each other. And that's going to allow me to solve for my pressure value. My new pressure value, P2, that's the unknown value, is P2. But what I can also realize is I'm not changing my number of moles. So N1 is the same as N2. T1 is the same as T2 because this is isothermal, constant temperature. My R value is exactly the same because R is R. That's not changing. So those three terms, N, R, and T, are all the same. They all cancel each other out. So what I'm really left with is P1, V1 equals P2, V2. Okay. So here's where if I recognize from the question that I'm holding temperature constant and my number of moles constant, that tells me that of my three fundamental laws, I'm really looking at Boyle's law. And Boyle's law says P1, V1 equals P2, V2. Okay. So either way gets me to this equation. It's just a matter of can I jump right to it if I recognize that this is a Boyle's law question, or do I have to just do a little bit of manipulation with our ideal gas law to get down to it? Either way works. Either way gets you to the same equation. And now we can take our values, plug them in for P1, V1, P2, V2, and solve for our new pressure. So our initial pressure of 1 atmosphere times our initial volume of 100 cubic centimeters is equal to our new pressure, P2, times 20 cubic centimeters. Here, I don't need to change my volume units. As long as they match cubic centimeters in both cases, that's fine, because I don't have an R value. R has a set unit of units for volume at liters, but if R isn't included, the units don't matter, just that they match. That's all that we care about here. So solving this for P2, I get a value of 5 atmospheres. So D is my correct answer here. All right. So this was now starting to bridge a little bit of conceptual as well as the mathematical to this question. Okay. Okay, let's look at this question. Which of the following gas samples would have the largest volume if all the samples are at the same temperature and pressure? So go ahead, hit pause, and work your way through this one. All right, so let's look at first off what's being held constant. We're looking at the same temperature and pressure. So if I take my ideal gas law again, PV equals nRT, temperature is the same, pressure is the same, R is a constant, that's always going to be the same. So what I'm really looking at here is the relationship between volume and number of moles. And if I look at that, they're on opposite sides of the equal sign. So that simply means as the volume goes up, so does the number of moles. So V and N are directly proportional to each other. This goes back to Avogadro's law, and that's what Avogadro was looking at, the relationship between volume and number of moles. And it said as one goes up, so does the other. So this question is really all about figuring out how many moles of my hydrogen gas, helium gas, or methane gas that I have. And whichever one of these values has the largest number of moles, that's going to correspond to the largest volume. So that's all we need to do here is just some conversions from whatever units we're starting with to moles. So let's look at option A. 9.0 times 10 to the 23 molecules of hydrogen. We'll convert that into moles just by using our Avogadro's number of 6.02 times 10 to the 23 molecules per mole. That gets me 1.5 moles of hydrogen gas. For helium, 8.01 grams. So I'm going to divide that by the formula weight, 4 grams per mole. That gets me 2 moles of helium. Methane is already in moles. I don't have to convert that. I've got 0.309 moles. So D is clearly not the right answer because these are all different numbers. And I just want to pick the one with the highest value. And that's going to be B, helium. Okay. Let's move on to this one. Submarines use potassium superoxide, KO2, as an air purifier because it reacts to carbon dioxide to release oxygen. So let's calculate the mass of potassium superoxide needed to react with 50 liters of carbon dioxide at 25 degrees Celsius and 1 atmosphere. So hit pause, work your way through, and let's see how we're doing on this one. All right. So we start with PV equals nRT. We're going to rearrange that to number moles. So I'm going to divide both sides by R and T. So number moles is PV divided by RT. So now it's just a matter of getting things into the right unit. So we'll convert our temperature to Kelvin. So I'm working with 298.15 Kelvin. I have everything else is set. My volume is in liters. My pressure is in 1 atmosphere. So 1 atmosphere times the 50 liters, P times V, divided by R, 8.205 times 10 to the minus 2, times our temperature of 298.15 Kelvin. And that gets me an N value of 2.04 moles. So that's moles of carbon dioxide, remember. So that's the trick with this one. Okay. So we started with an amount of carbon dioxide, 50 liters of carbon dioxide. So that's the moles I find. So now I have to just do a conversion from carbon dioxide to KO2, potassium superoxide. So let's just go ahead and do that. So looking at our stoichiometry here, 4 moles of KO2 equal 2 moles of CO2 equals 2 moles of potassium carbonate and 3 moles of oxygen. So I can take my 2.04 moles of carbon dioxide that we previously calculated, convert that to potassium superoxide by our 4:2 molar ratio. That gets me 4.08 moles of KO2. Now I'm ready to take that 4.08 moles of KO2 and convert that to grams. So just number moles times the given formula weight that was given in the question, 71.1 grams per mole. I get a value of 290 grams of superoxide. So looking at this, the correct answer here would have been A. Okay. This one was a tricky one because we have to recognize that we're starting talking about one compound and we're finishing our answers and talking about a different compound. So at some point when I recognize that, I know I need to do some kind of stoichiometric conversion using those coefficients from the balanced chemical equation to switch from talking about carbon dioxide initially to potassium superoxide at the end. Okay. All right, last question. If the pressure of a confined gas is doubled while the temperature remains constant, which of these 5 statements is correct? Hit pause, work your way through this, and let me know what you come up with for an answer. Okay, so we can do this utilizing 2 different versions of our ideal gas law, one at the first pressure, one at the second pressure. So I just write my ideal gas law in terms of P1V1 equals N1 RT1, and then P2V2 equals N2 RT2. So we've got 2 different versions depending on which pressure, our initial pressure or our second pressure. So we can divide one into the other so we can compare them. And what I see with what's being held constant, our N values cancel off because we're not changing the number of molecules. Our T values and our R values are not changing because we're not changing either of those. So those all go away. So what we really have here is a relationship of P1V1 equals P2V2. All right. And then we see so we can solve for V2. Just divide both sides over by V2. And then I see from our question that P2 is simply double P1. So I can replace P2 in my denominator with 2 times P1 in my numerator. Because again, the question says the pressure of a confined gas is doubled. So whatever my initial pressure is, I don't care what that number is, my new pressure is twice that value. It's twice the initial P1 value. So now that I have this, P1s cancel off, I really have V1 equals 1 divided by 2. So the correct answer here is B, the volume will decrease 1/2 of the original volume. Okay, we'll leave things here. There's a whole bunch of examples to let you get comfortable with using the ideal gas law in terms of calculations, as well as a little bit more conceptually. That's kind of what we did here, and looking at some of the complexities that can crop up with this ideal gas law. If you have any questions at all, please don't hesitate. I'm happy to hear from you. Take care. Thanks, everybody.